In this video, I'd like to go over mathematical models, specifically exponential and logistic models. Before I go over the examples, though, I just want to mention what we mean by models, mathematically speaking. Essentially, what we're looking for is developing a function or an equation based on real-world data. What we want to keep in mind with models is that because we're basing it off real-world data, our answers are not exact. What we're trying to get are approximations. We're trying to notice trends about what's happening, using the model to maybe predict what we would expect to happen if those trends continue. First, I want to talk about exponential growth. So exponential growth looks like the traditional exponential graph. So it increases, and it increases pretty rapidly. And an equation, or one way to write an exponential growth equation, would be n of t is equal to, right over here, and we would say that's n naught or n sub 0, which basically means it's the initial amount or the initial number. Whenever we have that little 0 there, it's referring to an initial value. E to the kt. So k is our growth rate and t is the time, whatever time we're dealing with. One thing to keep in mind for the k value is that the percentage would be converted to the decimal. So if we were talking about a 35% growth, we would write that as a k value of 0.35. So some types of examples that you might see that use exponential models would be things like population growth and bacterial growth. I want to work on creating an exponential model for population, and I'm going to use some of this US population information. So here I've got a table with the year and the population in millions, and also the growth rate. So the first graph I have here is spread out because I'm covering more years. I'm starting at 1800 here. And the reason I wanted to plot all of these points is because I think when you plot more points, you can kind of see a little bit better that the graph resembles an exponential graph. Of course, I do want to mention, though, especially since in more recent years, the growth rate has not been as high as in previous years. That's one reason. But if I do plot just from 1950 to 2020, it does sort of look like a line when I plot it that way. But if you do put it all together, you get something that looks a little more exponential. And so for the purposes of the example that we're going to do in this video, I'm going to treat the population growth as exponential, but I am going to use some of the more recent data to try and give a better approximation for the actual model. And so there's a lot that goes into modeling. Here, we're going to try and keep it a little bit more simplified. So if we're going to try to come up with our mathematical model, I'm going to write the equation again. The way to get our answer is we need to figure out this initial amount and the growth rate. And once we find those values, then we have our model. So first I want to just figure out which years to use. So maybe I'll use a spread of years here. Let's say we want to use, let's maybe start at 1980 to 2020. Let's say we're going to narrow in on those values. So if we do it this way, we would say that our initial year is 1980. And you could have like the t value in this case be 1980, but typically what we do is we readjust it. And so what we're going to do is actually let t be the years since 1980. So that means when t is equals 0, that means when t equals 0, that's going to represent the year 1980. And then if we wanted to look at it as an ordered pair, that would be t is our independent variable where there's usually an x, and the y is going to be the population. And I'll just write that in this case as n of t. So we can write that first point as 0, comma, and then what is the population in 1980? 226.5 million. So we've got one ordered pair. And then we can go ahead and take another ordered pair, and we're going to use that to find the growth rate k for our model. So we have some growth rates here. I'm not going to use those. I'm going to use this exponential model instead and get our sort of average growth rate from that. So let's pick another point. Let's say we pick the year 2020. So if we pick the year 2020, we need to figure out what our new t value is. So since t is the years since 1980, we can go 2020 minus 1980 to figure out how many years since we're dealing with. So in that case, it would be 40. So another ordered pair we have is 40, comma, and then the population in 2020 is 332.6. Okay, so let's go ahead and create our mathematical model. Okay, so if you can, you first want to try to plug in your initial amount. So if you know the value that you're starting with, you can just go ahead and plug it in here. And the starting value is when the x or the t value is equal to 0. That's what you're looking to plug in here. And so in this case, I'm going to write it as n of t is equal to 226.5 e to the kt. Now we need to do a little bit more work to figure out what is this k value, which is our growth rate. So to figure that out, we actually use the other point that we have. So remember, this is t is equal to 40, and n of 40 is equal to 332.6. So I'm going to plug that in. So I'm going to set the whole thing equal to 332.6. And leave k alone because that's what we're trying to figure out, and then plug in our t value or time, which we have as 40. And then we can go ahead and solve this exponential equation. So in this case, the first thing we'd want to do is divide. So we can go ahead and divide both sides by 226.5. And so on the right side, the 226.5 divided by 226.5 just goes to 1. And I'm going to go ahead and plug in what we end up with on the left. So that's about 1.468. Whenever I'm working on a problem, I try to keep a lot of decimals so that I don't end up with a rounding error at the end, which happens if you round too early in your problem. So I actually wrote like 1.468 here, but on my calculator, I'm actually going to keep track of the full value that's in my calculator and use that so I don't end up with any rounding errors. Okay, so then on the right here, we have E, and then I'm just going to write that as 40. Okay. At this point with solving this exponential equation, what you could do at this point, one way to do it is to think about it as taking the ln of both sides, and what that does is there's the property right here that if you have ln of e to an exponent, it's almost like what's happening is that the ln and the e are sort of canceling each other out. And you can also think about it as allowing you to bring the exponent to the front. And ln of e is just equal to 1. So when we apply this here, using that solving property, we get ln of 1.468. is equal to, and then basically on the right side, that is going to simplify to 40k. So then the last step is to divide by 40. And I'm going to plug that into the calculator. And I get about 0.0096. Now I'm going to go ahead and plug it in to get our final mathematical model. Now I'm just going to plug in some values into this model to see how well it approximates the information from our table. So into the model, I went ahead and plugged in the values of 10 is equal to t, 20 is equal to t, and 30 is equal to t. And so that correlates with the years 1990, or corresponds with the year 2000 and 2010. And so if we go ahead and look at our table here, just to kind of compare our results, we kind of see that we get answers. They're not the same, which is really to be expected with a model, but we see that they're kind of in the general ballpark of what the actual population values are. So we see the populations for 1990, 2000, and 2010. And so the model's kind of showing it seems to be pretty close to the population values in the last few decades. So then what we might use is the model to predict future populations. So if we did that, we could plug in something like what might the population be in the year 2040. And for that, we would plug in t is equal to 60. And I get approximately 402.9. And remembering the units would be million in this case. So this would be our approximation. And one thing to keep in mind with using models is that the further you go out in the future, then the less reliable the model would be, just because you would expect that things might change. And so you want to use the most current data, and then just kind of keep in mind that the further, like if I tried to plug in something like t is equal to 500, I'll get an answer, but it's not really one that I can perhaps rely on actually happening that far in the future.